All right, so second part of 15.4. All right, so we did a problem yesterday when we were working with Green's theorem. We did an example where we applied Green's theorem, and our double integral that came out of Green's theorem gave us, we ended up just finding the area of a region. So we're going to exploit that kind of idea for the first part of what we're doing today. So when we stated Green's theorem, we said that Green's theorem tells us that the integral around a closed path of m dx plus n dy was the double integral over the region enclosed by the path of dn dx minus dm dy over that region, where our vector field is mi plus nj. The Green's theorem tells us this. If, and this is what happened in our example, if this quantity is 1, the double integral and the line integral just becomes the integral of over r of dA, which is just the area of the region. So if we could pick, if we're trying to find the area enclosed by some simple closed curve, and we can pick m and n such that this quantity turns out to be 1, then we can find the area of that region by evaluating a line integral rather than evaluating a double integral. And sometimes evaluating that double integral to find the area can be difficult. So if we can pick our m's and n's so that this quantity comes out to be 1, we can find the area with this line integral. So to do that, we're going to be smart, and we're going to be smart, yeah. We're going to think. That's when I was doing an AP review session a couple weeks ago. I said, so how are we going to approach this problem? And someone said, you think? So we're going to think, and we're going to say let m equal negative y over 2, and n equals x over 2. So then if we take these partial derivatives and this difference, we just end up with 1 as our integrand. And then we can use this line integral to find the area of our region.
Can we get 1? That would be...
But the n dx, partial of n is 1/2. This is 1/2, and we're subtracting negative 1/2. A negative times a negative.
If you want a negative, you want it equals 1. That's
I'm sorry?
where you have the root if dn dx minus dn dy, and you can write equals 1.
Oh. There we go. All right. So this is how we're going to use Green's theorem to find areas. So we're going to state this as our theorem. And we're going to have a complicated setup because we have to have certain conditions. So we have our region R, and it needs to be bounded by a piecewise smooth so we can put a bunch of curves together. Simple closed curve. and we'll call C, is given by, and we're just going to write our line integral with m and n here. Our area equals a line integral around our curve. And I'm going to put this 1/2 in front, minus y dx plus x dy. And we could also write this. This is the same as saying the integral around our curve of minus y dx. And that is the same as saying the integral around our curve of x dy. And for this case, we're saying that n is 0. And by the three lines, I mean it's identically 0. It doesn't evaluate to 0. It's 0 everywhere on that curve. And for this one, we're saying that m is identically 0. So we're being smart again and picking our m's and n's so that when we take the two partial derivatives, our sum turns out to be 1. You could use it all the time, but if you have, we'll do an example where we would want to use it because evaluating the double integral is very difficult. So to find the area, we want to find the area enclosed by this curve, and the double integral is really difficult. We can turn it into evaluating the line integral around that curve. And that is often easier in those cases. So this is how we can use Green's theorem to find the area of a region. So let's look at one example, and then I want to talk about some extensions of Green's theorem that kind of preview what we're going to do for the rest of the chapter. And that's a part of this lesson that I'm really excited about. So any questions on this and why it works?
So what are you even doing there?
What's that?
What are you even doing?
We want to find the area enclosed by the curve.
And why it is separating if you do that?
Which part?
Down there.
Here?
Yeah.
Oh, so here I'm saying that that n is 0 and m is minus y.
Why can you do that?
We're just picking m and n so that when we do these partial derivatives, that this difference turns out to be 1. So our double integral gives us the area of the region, and that's the same as that line integral.
So is this for just like you're saying there's a theoretical case where we're going to make it, or is this like always going to be negative y and f?
Always. So we're just picking m and n such that when I do this the difference between these partial derivatives, I get 1.
How does that m and n work for any area?
Because when I take the partial of n with respect to x, subtract the partial of n with respect to y, I get 1.
The Green's theorem part of it,
Right.
how they cancel on equal 1. I don't get why you can pick m and n as those two things for any region you're given.
Because we're accepting Green's theorem as true. So if we're accepting Green's theorem as true, as long as as long as we get 1 here, that gives us the area of the region. So it doesn't matter what the region is, as long as as long as this quantity comes out to be 1, this line integral is the same as the area of the region.
Aren't m and n defined by our path of our function, not chosen by it?
Well, m and n aren't defined by the function, or I mean by the path. Usually we're given some function, we're saying evaluate this line integral of this function over this region.
So wouldn't that
So,
give
this, in what we're doing here is we're saying, rather than being given a function, given f, our problem, basically we're running Green's theorem in reverse. Our problem is find the area of this region.
Okay, and so
And
we're just picking a function that would give us m and n.
We're picking a function that would give us m and n. We're picking f so that this comes out to be 1.
So we're starting with the double integral.
We're starting with the double integral. Yeah, so we're going backwards really. We're starting with the double integral,
That makes sense.
and we're saying let's try to do that double integral as a line integral using green terms. Okay?
Yes.
All right. Glad we cleared that up. So yeah, we're using Green's theorem in reverse. All right, so let's look at an example. So we want to find the area bounded by, and we have this vector valued function r. So we want the area bounded by this curve, the graph of this curve between negative square root of 3 and square root of 3. So if we don't happen to know what this looks like, if we graph this, what I did was graphed it in my calculator for Wolfram alpha. And what we find is this graph, just a rough sketch, looks something like this. I want to do this in red. And this is x equals square root of 3. So as we go from negative square root of 3 to square root of 3, we traverse around this loop one time. So this is kind of an interesting little curve here. If we wanted to find the area bounded by this curve, to use the methods that we've used so far to do this as a double integral, or so if we were thinking of a double integral, we would have to find y in terms of x or x in terms of y. Well, with these two, with the x component being this and the y component being that would be, one, it would be difficult, and two, your result would turn out to be pretty ugly to find, to express this in a way that you could use a regular integral to find that area. So we're going to use Green's theorem. So we want the integral, double integral over r of dA. And just looking at that, I'm thinking that's going to be messy and difficult. Well, we have a region. Here's R. Simple closed curve. So we're going to use Green's theorem. And we're running, like we said, like we just talked about, we're going to run Green's theorem in reverse. So we said in reverse, running Green's theorem in reverse, the region of R, the double integral over a region R dA is 1/2 the integral around our boundary of minus y dx plus x dy. It's that line integral. So this, now I'm thinking this is not going to be too bad. X equals t squared from our parameterization of our curve. So dx is 2t dt. And y equals t cubed over 3 minus t squared. So dy is t squared minus 1 dt. Oh, minus 2t. Thank you. So this line integral is not looking too bad. We just end up with polynomials. So our area equals 1/2 the line integral around C, and I'm going to write this as, so this is going to be from minus square root of 3 to square root of 3 of y dx. So I get t cubed over 3 minus t squared, negative y, yes, minus t squared times dx, which is 2t dt, plus x t squared times dy times t squared minus 2t dt. So when t equals negative 3, I get t cubed, or sorry, t squared I, which is square root of 3, and I get square root of 3 over 3, negative square root of 3 over 3 minus 3j. Is that right? 3 root 3 over 3, there we go. Minus square root 3. Right. So we end up with 0j. So we're at square root of 3i and 0j.
Wait.
Yeah, how do you get 0j?
Could you get 3 root 3 over 3 minus 3?
But 3 root 9 over 3.
Minus 3.
Oh, yeah.
Is our curve, did we set up our curve wrong?
Should be minus 2.
Oh, this should be, that's why I had a 1 here. This should be t. That's why I wrote 1. So this should be t. I'm glad we caught that. Thank you. So y is t cubed over 3 minus t. Thank you, Cole. And then this dy would be t squared minus 1. And then this is t, and this would just be t squared minus 1. There we go. All right. Now does it make sense how we get the full loop?
Yes.
Yes?
Yeah, I wasn't thinking that way before.
Okay. Well, because you asked a question, we figured we fixed my mistake. All right. So, and then if we plug in square root of 3, we end up back at square root of 3i and 0j. All right. So now we've got this integral set up properly. Now if we evaluate it, this comes out to, if we could evaluate, this is just polynomials, not difficult to evaluate. I plugged it into my calculator, and the approximate answer is 2.77 square units. We could also find this same result. It's probably a little easier. We could say that the area is the integral around C of x dy, which is just the integral from minus square root of 3 to square root of 3 of t squared times t squared minus 1 dt. And that also comes out to about 2.77. This one's a little easier.
Why does that work?
What's that?
Why does that work?
So for this one, let me go back here. We're saying that n is 0, or m is 0, and n is just x. So dn dx here is 1. So then this quantity turns out to be 1. So that integral evaluates at about 2.77, or Not necessarily. It
Is that
just-
why there's the 1/2 out front?
that's why there's 1/2, because we did the two pieces.
They're each the same.
They turn out to be the same. And we could also say minus y dx, which is the integral from minus square root of 3 to square root of 3, not quite as easy, of negative t cubed over 3 minus t times 2t dt. And this one also evaluates to about 2.77. So we could use any of those three expressions to find the area of our region. The second one would probably be a little easier. But to find it, we have to find x, dx, y, dy. I guess we didn't have to find dx here, but we needed x. And we had to find dy. So this is how we can use Green's theorem running in reverse to find area, as long as we write our parameterization of our curve correctly. It'll give us a correct one. Questions? All right, so now we're going to get to the good part, what I think is the good part of today. Some alternate forms of Green's theorem that kind of preview what we're going to do for the rest of the chapter. That is an N, yes. All right. So what we're going to do for this alternate form of Green's theorem is we're going to let our vector field, we're still in the plane. Green's theorem only applies in the plane. We're going to let our vector field be mi plus nj plus 0k. So our field is still in the plane, but we're thinking of it as a three-dimensional vector. So we're going to take the cross product. We're going to find the curl of f. So the curl of f is this determinant of m, n, and 0. If we form this cross product, we get minus the partial of n with respect to z, I hat, plus the partial of m with respect to z, j hat, plus this quantity. Does that third quantity look familiar? That's the quantity we've been talking about in Green's theorem, right? So that gives us a hint of why we did this. And what is dn dz and dm dz? 0. We're in the plane, so that's 0. What we're going to do here is take the dot product. So it's okay. What we're going to do next, we'll take care of that. So we're going to take the dot product if m or n does have a z in it, and we'll get to that later, but what we're going to do here is take the dot product of the curl with k hat. So we're finding the vertical components of the curl. So these don't, when we do our dot product, these don't even come into play. So we take the dot product with the k hat vector, and we just end up with this quantity. So this is the vertical component of the curl. And then we can use this to write because this is our quantity in Green's theorem, that the line integral around C of m dx plus n dy, and that is the same as saying the line integral around C of f dot dr. This is the differential form, this is the vector form, equals the double integral over our region of del cross f dot k hat dA. So what we're saying here is that the line integral of f around the boundary, and the line integral gives us the tangential component of f around the boundary, so we're summing the tangential component of f around the boundary, equals the double integral, the sum of the normal or the vertical component of the curl over the region. So the sum of the tangential component of f around the boundary of this region equals the sum of the vertical component of the curl over the region.
How is that? Why?
So, and what we're going to do is this is when we talk about this in 3 dimensions. This is Stokes theorem. So, and we'll give an interpretation of the curl once we get to this in 3 dimensions. But what it's telling us is that the normal component of the curl, the vertical component of the curl, tells us the tendency of the field to cause a circulation around the boundary. So the vertical component of the curl tells us the tendency of the field to make a circulation around the boundary of that region. So that kind of gives us a hint of what the curl is telling us about our field. And we'll do some more with this idea at the end of chapter 15. So this is just kind of a little preview. So again, the sum of the tangential component of f around the boundary is equal to the sum of the vertical component of the curl over the region. So this is telling us about the curl tending to cause a circulation, a rotation around the boundary of that region. All right, questions?
Well, the dot product that you did,
Mm-hmm.
how did that's just something? How does the do it?
Yeah, so we did the dot product because this is,
But you should do that times that. Essentially, what you were saying.
well, when we take the dot product, it's the I component of this vector times the I component of this vector, 0. The j component of this times the j component of that vector is 0. The k component of this times the k component of that vector, which is just this times 1.
It's just a way to.
Yeah, so we're just isolating this quantity.
We're just assuming it's 1 because
What's that?
well, why is that 1?
K hat? K hat, the magnitude of k hat is 1. K hat is 1 k hat.
Oh, just no k.
Yeah, just normal k hat. Right. Okay.
Oh, you thought you was a k from the
No, this is our standard unit vector. Okay? All right. So we're going to look at a similar expression for the normal component of f in the plane. So this is when things are really, this is kind of the culmination of the entire chapter, is what we're talking about here when we extend this to 3 dimensions. All right, so let's let our curve be given by this vector valued function. R equals some x of ti plus y of t j. So that's the boundary of our region. A less than or equal to t, less than or equal to b. So we have this bounded region. R is the boundary in our region. Our unit tangent vector for this curve is r prime, if we remember back to when we did talked about unit tangent vectors, over the length of r prime. And with this expression, it's going to be x prime over the length of r prime I plus y prime over the length of r prime j. The outward So the outward unit normal vector n, we're going to switch the 2 components and change the sign on one, and we want to make sure we get that outward unit normal vector. So n is going to be y prime over the length of r prime minus x prime over the length of r prime. This is I and j. So this is going to give us an outward unit normal vector. And if you, to convince yourself that this is the outward unit normal vector, if we draw our curve, some curve like this, if this is t, that is going to be n. And if you look at the components here, you can see that in order to get our outward unit normal vector, we need to switch our signs this way. All right, and we're going to let our f, our field, equal mi plus nj again. And we're going to form the dot product. We're going to find the line integral around C of f dot n. So we're going to sum the normal component of f around this curve. That's going to be the integral from a to b of mi plus nj dot this quantity. ds. So we're summing the normal component of f around our curve. And this is going to equal, when I form that dot product, the integral from a to b of m y prime over the length of r prime minus n x prime over the length of r prime times ds. But what does ds equal? How we express ds in the past? Magnitude of r prime dt. So we're going to express ds as the magnitude of r prime dt, and then we can rewrite this integral. So our integral equals the integral from a to b the r primes cancel, and I get m dy dt minus n dx dt. See where we're going now? dt.
How do you get it to cancel? Okay, why is it the x and
Y prime is
y?
y prime is dy dt. X prime is dx dt. Right? So this equals the line integral around our closed curve of minus n dx plus m dy. And by Green's theorem, we have the double integral over r of dm dx plus dn dy dA. So we're saying that this is our first function, that's our second function. So this is, by Green's theorem, we end up with this quantity. What is dm dx plus dn dy? Anybody recognize that quantity?
Doesn't Green's theorem dn minus dn?
So by Green's theorem, we would take the partial of this.
Oh, but then it's negative.
Right.
Negative, right.
Mhm,
Okay,
mhm.
so
So we're taking the partial of this with respect to x and subtracting the partial of this quantity with respect to y. So then
divergence, del dot f.
this is del dot f. That's the divergence of f. So finally, so the line integral around our closed curve of the normal, outward unit normal component of f equals the double integral over our region of the divergence of f. So the line integral of the normal component of f around C is equal to the sum of the divergence of f over the region. So the divergence is telling us the tendency of the field to cause an outward flow in our region. So we're summing the outward normal component of f, and that is equal to the divergence of f over our region, the sum of the divergence of f over our region. So the divergence is telling us the tendency of this field to cause an outward flow on the boundary.
What is integral to C of f dot mds again?
This is the sum of the normal, outward unit normal component of f around the boundary. So we're taking the dot product of f with the outward unit normal component, so that gives us the outward component of f around the boundary. We're summing that around the boundary. And this is the divergence theorem that we'll talk more about in 3 dimensions. So a couple of nice vector derivations here. All right, any questions? Whoops. Did I just... Oh, there we go. All right, homework. Homework doesn't have anything to do with what we just talked about. That's a preview. Homework has to do with finding
The
area.
last thing we finally got to.
What's that?
The important part of that was just the last.
The last thing that we got to, yes. We will have homework that has to do with the Divergence Theorem and Stokes Theorem later. I just wanted to give you a preview.
Why didn't you come?